Drill down through kilometers of compacted snow and ice, and you're reading a record of Earth's climate and atmospheric composition going back hundreds of thousands of years. Every volcanic eruption, every major wildfire, every shift in ocean circulation, every asteroid impact or comet airburst leaves traces in the ice, and if you know how to read those traces, you can reconstruct events that happened long before humans invented writing, before we built cities, before we even figured out agriculture. The Greenland ice cores have been studied for decades. Multiple drilling projects, different sites across the ice sheet, each one adding detail to our understanding of how climate has changed over deep time. The GISP2 core, the NGRIP core, the NEEM core. Scientists have analyzed them for temperature proxies, for atmospheric gas composition, for evidence of past volcanic eruptions and cosmic impacts. They've found the chemical fingerprints of catastrophes we knew about from other sources, and they've discovered catastrophes we had no idea occurred. It's detective work on a geological timescale, piecing together Earth's history one ice layer at a time. One of the most dramatic events visible in the ice core record is the Younger Dryas. That's the name given to a sudden cold snap that hit the northern hemisphere about 12,800 years ago. The world had been warming, coming out of the last ice age, glaciers retreating, forests spreading, and then, abruptly, temperatures plunged. Not gradually over centuries, but fast enough that the climate shift happened within a human lifetime. The cooling lasted for about 1,200 years before temperatures rose again, just as suddenly. In the ice cores, the Younger Dryas shows up as a distinct layer with different isotope ratios, different dust content, different chemical composition than the ice immediately before or after. The cause of the Younger Dryas has been debated for decades. The mainstream explanation involves changes in ocean circulation, specifically the shutdown of the Atlantic meridional overturning circulation due to massive freshwater input from melting ice sheets. Basically, so much cold freshwater poured into the North Atlantic that it disrupted the ocean currents that normally carry warm water northward, triggering a climate flip. That mechanism makes sense. It's supported by oceanographic evidence, and it fits with what we know about how the climate system can shift between different stable states. But there's another hypothesis, more controversial, more contested by mainstream paleoclimatology, the impact hypothesis. The idea that the Younger Dryas wasn't caused by internal climate dynamics, but by an external trigger, specifically a comet or asteroid impact or airburst over the North American ice sheet. Proponents of this idea point to a layer in the geological record right at the Younger Dryas boundary that contains unusual materials, nanodiamonds which can form under the extreme pressures of impacts, magnetic microspherules, tiny beads of melted rock, iridium anomalies though not as strong as the ones associated with the dinosaur-killing asteroid, and elevated levels of certain platinum group elements that are more common in extraterrestrial materials than in Earth's crust. The impact hypothesis has been controversial since it was first proposed in 2007. Critics argue that the evidence is ambiguous, that many of the supposed impact markers can form through other processes, that there's no confirmed impact crater of the right age. Supporters counter that an airburst or impact over the ice sheet wouldn't necessarily leave a crater, that the evidence is stronger than critics acknowledge, and that the timing fits too well with the climate shift and with mass extinctions of North American megafauna to be coincidental. The debate has gone back and forth for nearly 2 decades, with neither side fully convincing the other. And then, in late January of this year, a team analyzing samples from the NEEM ice core found something that nobody expected, something that doesn't fit into either the mainstream ocean circulation model or the standard impact hypothesis, something that connects the Younger Dryas event to 3I/Atlas. The NEEM project, the North Greenland Eemian Ice Drilling Project, completed its main drilling operations back in 2012, reaching a depth of 2,537 meters, and recovering ice dating back more than 128,000 years. But the analysis of those samples is still ongoing. Ice core science is slow work. You can't just pull up a cylinder of ancient ice and immediately read everything it contains. Different types of analysis require different techniques, different instruments, different expertise, and there's only so much sample to work with, so you have to be careful about what analyses you run and in what order. Dr. Henrik Sørensen from the University of Copenhagen has been part of the NEEM analysis team since the beginning, specializing in trace element geochemistry. His work focuses on identifying microscopic particles embedded in the ice, figuring out where they came from, what they tell us about atmospheric composition and transport patterns in the past. In late 2025, he was working on samples from the depth interval corresponding to the Younger Dryas boundary, specifically looking at the composition of dust particles and aerosols trapped in that layer. Standard procedure for this kind of analysis involves melting small sections of ice core under clean conditions, filtering out the solid particles, and then analyzing them with various spectroscopic techniques. You can identify mineral compositions, trace element abundances, isotope ratios. It's painstaking work, each sample taking days or weeks to fully characterize, but it builds up a detailed picture of what was in the atmosphere when that ice formed. Sorensen noticed something odd in the samples from right at the Younger Dryas onset. The dust particles had unusual compositions, not quite matching the typical windblown material from Asian deserts or North American glacial till that you normally see in Greenland ice cores. There were elevated abundances of certain elements, carbon compounds with unusual molecular structures, isotope ratios that didn't fit the expected terrestrial sources. At first, he thought it might be contamination, something introduced during the drilling or handling process, but the anomalies were consistent across multiple samples from the same depth interval and absent in samples just above or below, which argued against contamination. He ran more detailed spectroscopic analysis using techniques that can identify specific molecules and their structures, and he found organic compounds that looked extraterrestrial. Not just organic compounds in general, which can form through all kinds of processes, but specific molecules with isotope ratios and structural characteristics that match what we see in cometary materials. Carbon monoxide with a particular carbon-13 to carbon-12 ratio. Complex organic molecules like formaldehyde and hydrogen cyanide at elevated concentrations, trace amounts of what appeared to be nitrogen-bearing compounds with deuterium enrichment. If you've been following the 3I Atlas story, those molecules probably sound familiar, because they're the same compounds in similar ratios that spectroscopic observations detected in 3I Atlas during its passage through the inner solar system in 2025. The comet's spectrum showed strong carbon monoxide emission, organic molecules, unusual isotope signatures that distinguished it from typical solar system comets. And here were those same chemical fingerprints, frozen in Greenland ice 12,800 years old. Sorensen didn't immediately make the connection. He's a paleoclimatologist, not an astronomer following interstellar comets. His first thought was that he'd found evidence supporting the Younger Dryas impact hypothesis, that these extraterrestrial materials in the ice core represented fallout from a comet airburst. He wrote up his preliminary findings, prepared to submit them to a geoscience journal, mentioned the results at a workshop on ice core paleoclimatology in December. Dr. Emma Richardson from MIT was at that workshop. She works on ice core chemistry, but also has a background in cosmochemistry and had been following the 3I Atlas observations with interest. When Sorensen presented his data, showing the spectroscopic signatures of the organic compounds he'd found, Richardson recognized the pattern immediately. She'd seen those exact same molecular fingerprints in the spectroscopic data from 3I/Atlas, had even co-authored a paper analyzing the comet's unusual carbon monoxide to water ratio and its organic molecule abundances. After the presentation, she approached Sorensen, asked if he was aware of the 3I Atlas spectroscopy results. He wasn't. She pulled up the published spectra on her laptop, showed him the comparison. The match was striking. Not just similar, not in the same general category. The relative abundances of different carbon monoxide isotopologues, the ratios of various organic species, the deuterium enrichment patterns, they aligned within measurement uncertainty. The chemical signature frozen in the Greenland ice matched the chemical signature of the interstellar comet that had passed through our solar system 4 months earlier. That's when things got complicated, because if the match is real, if those compounds in the ice core really did come from something chemically identical to 3I/Atlas, it means one of two things. Either there was a different comet 12,800 years ago that happened by pure chance to have exactly the same unusual chemistry as 3I/Atlas, or 3I Atlas itself was there, in Earth's atmosphere, 12,800 years ago. Let's talk about what makes a chemical match meaningful, because this is where the finding goes from interesting coincidence to something that demands serious explanation. When you analyze extraterrestrial materials, whether it's meteorites or samples from comets or particles collected from asteroid missions, you're looking at isotope ratios. Isotopes are versions of the same element with different numbers of neutrons. Carbon-12 and carbon-13 are both carbon, but carbon-13 has one extra neutron. The ratio between them varies depending on where and how the material formed. In Earth's atmosphere and biosphere, you get certain standard ratios. In materials from the outer solar system, the ratios are different. And in interstellar materials, materials that formed around other stars in different molecular clouds, the ratios can be very different. 3I Atlas showed unusual isotope ratios from the first detailed spectroscopic observations. The carbon-12 to carbon-13 ratio in its carbon monoxide emission was offset from typical solar system values by about 15%. Not a huge difference, but statistically significant, consistent with formation in a molecular cloud with different chemical history than the one that made our solar system. The deuterium to hydrogen ratio, measured in water and organic molecules, was also elevated compared to most solar system comets, again, pointing to an origin somewhere else, under different conditions. Those specific isotope ratios are what Sørensen found in the Greenland ice core samples, not just the presence of carbon monoxide or organic molecules, which could come from terrestrial sources or from any cometary material, but carbon monoxide with a carbon-13 enrichment matching 3I/Atlas's signature, organic molecules showing the same deuterium to hydrogen elevation. When Richardson compared the ice core data to the published spectroscopy from 3I/Atlas, the isotope ratios aligned within the measurement uncertainties of both datasets. That level of agreement isn't something you get by accident. Different comets have different isotope ratios depending on where they formed and what they've been through. Even comets from the same stellar system can show variations. To find materials in Earth's ice from 12,800 years ago that match a comet observed in 2025, match not just in general chemical composition, but in specific isotope ratios that vary from one object to another, that's a fingerprint, that's identity. Dr. Sørensen and Dr. Richardson spent the next month running additional analyses, bringing in collaborators from other institutions, making absolutely sure the match was real and not some artifact of measurement or analysis. They reprocessed ice core samples from adjacent depths, checking if the anomalous isotope signatures appeared anywhere else in the core. They didn't. Only in the narrow depth interval corresponding to the Younger Dryas boundary, spanning about 2 years' worth of ice accumulation at that depth, did they find the 3I Atlas chemical fingerprint. They also analyzed samples from other ice cores to see if the signal was present elsewhere in Greenland, or if it was unique to the Nîmes site. The N-grip core, drilled about 300 kilometers away from Nîmes, had samples from the same time period already archived and partially analyzed. The team obtained permission to run new tests on those samples. Same result. The chemical markers appeared in the NGRIP core at the Younger Dryas boundary. Same isotope ratios. Same molecular signatures. 2 independent ice cores, different drilling sites, same anomaly. Then they looked at Antarctic ice cores, the WAIS divide, core from West Antarctica, the EDML core from Dronning Maudland. Antarctica is on the opposite side of the planet from Greenland. Different atmospheric circulation patterns, different deposition environments. If the chemical markers were from a global atmospheric event, something that affected the whole planet simultaneously, you'd expect to see traces in Antarctic ice from the same time period. The Antarctic cores from 12,800 years ago showed something, but it was different. There were elevated organic molecule concentrations, some isotope anomalies, but the signatures were less pronounced and the timing was offset by a few decades. That asymmetry is actually informative because it suggests the source of the materials was concentrated in the northern hemisphere, which is what you'd expect if something entered Earth's atmosphere over North America or the North Atlantic. The concentration of materials in the ice provides another piece of the puzzle. When you find traces of extraterrestrial materials in ice cores, the abundance tells you something about the scale of the event. A small meteorite airburst deposits minimal material over a limited area. A larger impact spreads debris across hundreds or thousands of kilometers. A truly catastrophic event can inject materials into the stratosphere, where they circulate globally and settle out over months or years. Sørensen's team calculated the total mass of 3 Salcon I/Atlas-like materials deposited in the Greenland ice based on the concentrations they measured and the estimated deposition rate. The numbers are uncertain because you have to make assumptions about how the materials were distributed and how much might have been lost to various processes, but even conservative estimates put the total mass at hundreds of thousands of tons, possibly millions of tons, of cometary material entering the atmosphere over a relatively short time period. That's not a small object. That's not a meter-sized boulder burning up in the upper atmosphere. That's something big. Now here's where it gets interesting. The materials in the ice aren't evenly distributed. They're concentrated in distinct peaks within the Younger Dryas boundary layer, suggesting multiple deposition events rather than one continuous input. The highest concentration appears in ice corresponding to roughly 12,800 years ago. Then there are smaller peaks over the following 10 to 20 years. It's the pattern you might expect if a large object broke apart in Earth's atmosphere or near Earth space, with the main fragment creating the primary deposition and subsequent fragments or debris creating smaller secondary peaks. Comet fragmentation isn't unusual. We've watched it happen in modern times. Comet Shoemaker-Levy 9 broke into multiple fragments before impacting Jupiter in 1994. Comet 73P/Schwarzmann-Wachmann 3 split into over 60 pieces observed in 2006. Comets are fragile, held together more by their own weak gravity than by material strength. If a comet on a close approach to Earth encountered strong tidal forces or atmospheric stress, it could easily break apart, scattering material across a wide area. The impact hypothesis for the Younger Dryas has traditionally proposed a single airburst or impact event over the North American ice sheet, but the ice core data, if it's really showing 3I Atlas materials, suggests something more complex. Multiple fragments, possibly spread across different times and locations, each depositing materials that eventually made their way into Greenland's atmosphere and precipitation. That kind of fragmented impact or airburst sequence could explain some of the unusual features of the Younger Dryas onset, why there's evidence of widespread burning and disruption but no single confirmed crater, why the cooling happened so fast but showed regional variations in timing and intensity. Dr. Mark Boslow from Los Alamos National Laboratory, who has done extensive modeling of comet and asteroid airbursts, got involved in the analysis when Richardson reached out to him. Boslow has been skeptical of the original Younger Dryas impact hypothesis, arguing that the evidence doesn't support a large, coherent impact, but when shown the ice core data and the isotope matches to 3I/Atlas, he acknowledged that a fragmented comet entering the atmosphere would leave exactly the kind of geochemical signature Sorensen found, and wouldn't necessarily leave the kind of crater or concentrated impact deposits that earlier searches had been looking for. He ran simulations modeling what would happen if an object the size of 3I/Atlas, roughly 400 meters to a few kilometers in diameter, entered Earth's atmosphere at interstellar velocities. The object wouldn't make it to the ground intact. At those speeds, atmospheric friction and ram pressure would break it apart at high altitude, maybe 50 to 100 kilometers up. Each fragment would generate its own airburst as it decelerated and exploded, creating multiple overlapping pressure waves, thermal pulses, and debris clouds. If the fragmentation happened over North America, with the object coming in at a shallow angle, fragments could be spread across thousands of kilometers, with airbursts over the ice sheet, over forests, over the ocean, each depositing materials in slightly different patterns. The total energy release would be enormous, equivalent to hundreds or thousands of nuclear weapons, depending on the object's size and entry velocity. That much energy dumped into the atmosphere over a short time would have catastrophic effects. Immediate thermal radiation would ignite wildfires across vast areas. Pressure waves would flatten forests, shatter ice, create seismic disturbances. The injection of massive amounts of dust and aerosols into the stratosphere would block sunlight, triggering rapid cooling. And if significant portions of the ice sheet were vaporized or melted, the resulting freshwater input to the North Atlantic could disrupt ocean circulation, providing the trigger for the longer-term Younger Dryas cooling. This scenario reconciles the impact hypothesis with the ocean circulation hypothesis. It's not either/or. The impact or airburst provides the initial trigger, the catastrophic event that disrupts climate and injects material into the atmosphere. The ocean circulation changes are the response, the feedback mechanism that sustains the cooling for over 1,000 years. Both processes are at work, connected by causation rather than being competing explanations. The evidence that originally supported the Younger Dryas impact hypothesis, the nanodiamonds and magnetic microspherules and platinum anomalies, fits into this picture. Those materials can form during high-velocity impacts or airbursts, created by the extreme pressures and temperatures. The black mat layer found at archaeological sites across North America, a dark, organic, rich sediment interpreted as evidence of widespread burning and environmental disruption, also fits. And now, the ice core data provides the chemical fingerprint, the direct connection to a specific source, 3I Atlas or something chemically indistinguishable from it. So now we have to face the obvious question. If 3I Atlas or something chemically identical to it was in Earth's atmosphere 12,800 years ago, and we observed it passing through the solar system in 2025, what does that tell us about its orbit? Remember, when 3I Atlas was first characterized, everyone assumed it was making a one-time visit, a hyperbolic trajectory that would take it out of the solar system, never to return. That assumption was based on its high velocity and the calculations showing it came from interstellar space. But if it was here before, if it shows up in the geological record from multiple time periods, then the whole interstellar visitor narrative needs revision. Dr. Alessandro Morbidelli from the Observatoire de la Côte d'Azur in France specializes in orbital dynamics of small bodies in the solar system. When the ice core findings were presented at a planetary science conference in early February, Morbidelli immediately started working through the implications. He took the observed 2025 trajectory of 3I/Atlas, the historical evidence from the Dead Sea Scrolls suggesting a passage around 5 BCE, and now this new data point from 12,800 years ago, and tried to fit them into a coherent orbital model. The math is complicated because you're dealing with multiple gravitational perturbations over enormous timescales. Every time an object passes through the inner solar system, it interacts gravitationally with the planets. Jupiter and Saturn especially can alter orbits significantly, adding or removing energy, changing the orbital period. Small changes per orbit accumulate over multiple passages, making long-term predictions uncertain. But you can work backward. Use the known data points to constrain what the orbit must have looked like. Morbidelli's preliminary models suggest we're not looking at a simple periodic orbit with a constant return interval. The data points don't fit that. From 12,800 years ago to 5 BCE is roughly 12,800 years. From 5 BCE to 2025 CE is about 2,030 years. That's a huge discrepancy, way too large to explain by measurement uncertainties or chronological errors. If it's the same object returning on the same orbit, the orbital period must have changed dramatically between the ancient passage and the recent ones. What could cause that kind of change? Gravitational interaction with a planet during one of the passages. If the object that caused the Younger Dryas event came in on a trajectory that brought it very close to Jupiter or Saturn, a close approach within a few planetary radii, the gravitational slingshot effect could have altered its orbit substantially. An object initially in a very long period orbit, maybe with a 10,000 or 15,000 year period, could be perturbed into a shorter period orbit, something closer to 2,000 years, by a single close planetary encounter. This scenario fits with the fragmentation evidence from the ice cores. If the object came in close enough to Earth to deposit materials in the atmosphere 12,800 years ago, it was also passing through the region where gravitational interactions with the inner planets would be strongest. A close approach to Earth, then a subsequent encounter with Jupiter on the outbound leg, could reshape the orbit significantly. The object might have broken apart due to tidal stress during the Earth encounter, with fragments following slightly different trajectories afterward, some captured into shorter orbits, others continuing on their original paths. That would explain why we see what appears to be the same chemical signature at widely different time intervals. Multiple fragments from the same parent body, each in its own orbit with different periods. One fragment might have a 2,000-year orbit, another a 4,000-year orbit, another still on an escape trajectory heading back into interstellar space. They all started as parts of the same object, so they share the same chemistry, the same isotope ratios, the same molecular composition, but they're now separate entities following independent paths through the solar system. This multi-fragment model also connects to the Euclid discovery of 47 objects with identical spectral signatures. Remember those? Scattered through nearby interstellar space, 6 of them on trajectories toward Earth with arrival times spread over the next few centuries. What if those aren't independent objects at all? What if they're all fragments of the same parent body that broke apart during its passage 12,800 years ago, scattered across a huge volume of space but all following related orbits that eventually bring them back toward the inner solar system? The fragmentation would have happened under extreme conditions, an object several kilometers in diameter encountering tidal forces from Earth's gravity, atmospheric stress as it grazed the upper atmosphere, thermal stress from solar heating. All of that acting together could shatter even a fairly cohesive body, breaking it into dozens or hundreds of pieces ranging from tens of meters to kilometers in size. Each fragment gets a slightly different velocity kick from the breakup, sending them on diverging trajectories. Over thousands of years, those small velocity differences add up to huge spatial separations. By now, the fragments are scattered across light years of space, but they're all still loosely gravitationally associated, all part of the same dynamical family. This is speculation, of course. We don't have direct evidence that the Euclid objects are fragments of a Younger Dryas impactor, but the pieces fit together in a way that's compelling. Chemical identity across dozens of objects, multiple pieces on Earth-crossing trajectories, historical evidence of previous passages, geological evidence of a catastrophic fragmentation event 12,800 years ago. It's circumstantial, but it's coherent. Now let's talk about what the Younger Dryas event actually did to Earth, because the ice core chemistry is just the fingerprint. The real story is in the archaeology and paleontology, the evidence of what happened to life on Earth when this object, whatever it was, entered the atmosphere. The Younger Dryas is marked by dramatic climate change, yes, but also by extinctions, cultural disruptions, environmental catastrophes that reshaped the planet. In North America, the end of the Pleistocene saw the disappearance of most megafauna species: mammoths, mastodons, saber-toothed cats, giant ground sloths, dire wolves, dozens of large mammal species that had thrived for millions of years all went extinct within a relatively short time window. The timing has been debated, whether the extinctions happened all at once or were spread over centuries, whether they were caused by human hunting pressure or climate change or some combination, but many of the extinction dates cluster right around the Younger Dryas boundary 12,800 years ago. The Clovis culture, the earliest widespread archaeological culture in North America, also disappears from the record at the Younger Dryas boundary. Clovis points, the distinctive stone tools that characterize this culture are found in archaeological layers below the black mat, but rarely above it. The people didn't disappear entirely, humans continued living in North America, but the Clovis culture as a distinct tradition seems to end abruptly. Archaeological sites show evidence of abandonment, disruption, a break in the continuity of material culture. In the Middle East and Europe, there are hints of similar disruptions. The transition from the Epipaleolithic to the Neolithic, the shift from hunter-gatherer societies to early agriculture, happened shortly after the Younger Dryas. Some researchers have argued that the climate stress of the Younger Dryas forced human populations to adopt agriculture as a survival strategy when wild food sources became unreliable. The archaeological site of Göbekli Tepe in Turkey, with its massive stone structures built around 11,000 years ago, appears just after the Younger Dryas ends. Maybe it's coincidence, or maybe it's a response, monumental architecture built by societies reorganizing after a period of catastrophic disruption. The black mat layer found at many North American sites is one of the most visible markers of the Younger Dryas boundary. It's a dark, carbon-rich sediment layer typically 10 to 50 centimeters thick, found overlying Clovis artifacts and extinct megafauna remains. The layer has been interpreted as the result of widespread burning and biomass destruction, possibly from wildfires, possibly from the impact or airburst of extraterrestrial materials. Chemical analysis of the black mat shows elevated concentrations of charcoal, burned organic matter, and in some locations the same kinds of impact markers found in the ice cores. If the ice core data is right, if 3I Atlas materials rained down on North America 12,800 years ago, the black mat is exactly what you'd expect to find. Airbursts would ignite massive wildfires across the continent, forests, grasslands, peat bogs all burning simultaneously, producing vast amounts of charcoal and ash. That material gets washed into lakes and streams, settles in archaeological sites, creates a distinct sediment layer marking the event. The fact that the black mat is found across such a wide geographic area, from Alaska to Mexico to the southeastern United States, suggests the triggering event was continental in scale, not a localized phenomenon. Lakes and wetlands from the Younger Dryas period show evidence of sudden environmental change. Pollen records indicate rapid shifts in vegetation, from forest to grasslands or tundra, happening within decades. Sediment cores show spikes in erosion, indicating landscape destabilization. Some lake cores contain layers of disturbed sediment interpreted as evidence of seismic shaking or massive flooding events. All of this is consistent with a scenario where multiple airbursts shock the landscape, ignite fires, disrupt ecosystems, and trigger secondary effects like erosion and flooding. The Carolina Bays, a collection of over 500,000 elliptical depressions scattered across the Atlantic coastal plain from New Jersey to Georgia, have been proposed as possible impact or airburst-related features. They're aligned in a pattern suggesting a directional source from the northwest, which fits with a fragmented object entering the atmosphere over the Great Lakes, a region, and scattering debris southeastward. Conventional geology has explained the bays as wind or water-form features, but the impact hypothesis for their origin has been revived in light of the Younger Dryas evidence. The publication of the ice core findings hit the scientific community like a shockwave in early February. The paper appeared in Nature Geoscience with a deliberately cautious title, Extraterrestrial Organic Compounds in Greenland Ice, coincident with Younger Dryas onset, show chemical affinity to interstellar comet 3I/Atlas. Cautious, yes, but the implications were anything but subtle. Within days, there were response papers being drafted, conference sessions being organized, research proposals being submitted to funding agencies. If 3I Atlas or its fragments were responsible for the Younger Dryas, if we can read that event in ice cores, what else might we find if we look harder? Multiple research teams immediately started reanalyzing geological and ice core records from other time periods, looking for similar chemical signatures. If fragments of this object have been passing through the inner solar system on various orbits over the past 12,000 years, there should be traces in the geological record. Maybe not as dramatic as the Younger Dryas boundary, smaller fragments wouldn't deposit as much material, but still detectable if you know what to look for and where to look. Dr. Sørensen's team at the University of Copenhagen expanded their analysis to other sections of the Nemesis core, particularly looking at intervals corresponding to known historical events that might have been triggered by impacts or airbursts. The Late Bronze Age collapsed around 1200 BCE, when multiple civilizations in the Mediterranean and Near East collapsed simultaneously. The transition between the Pleistocene and Holocene around 11,700 years ago, another period of rapid climate change. Various volcanic events and climate anomalies scattered through the Holocene that might have extraterrestrial components. They found hints, though nothing as clear as the Younger Dryas signal, a small concentration spike in organic molecules with unusual isotope ratios around 3,200 years ago, roughly corresponding to the Late Bronze Age. Another spike around 5,300 years ago with similar but less pronounced characteristics. These could be smaller fragments, objects tens to hundreds of meters in size rather than kilometers, depositing materials over more limited areas, or they could be unrelated, coincidental variations in atmospheric chemistry. The data is ambiguous enough that it doesn't prove anything, but it's suggestive enough to warrant deeper investigation. Lake sediment cores are another archive being re-examined. Lakes act as natural sediment traps, accumulating layers of material year by year that preserve chemical and biological signals. Dr. James Kennett from UC Santa Barbara, one of the original proponents of the Younger Dryas impact hypothesis, has been coordinating a multi-institutional effort to resample lake cores from across North America, specifically targeting sites that might have been in the path of the Younger Dryas airburst debris field. His team is using new analytical techniques that weren't available when many of these cores were first studied decades ago. High-resolution mass spectrometry can detect trace amounts of specific organic molecules. Isotope ratio mass spectrometry can measure tiny variations in deuterium, carbon-13, nitrogen-15. If there are 3 like Atlas chemical fingerprints in lake sediments from 12,800 years ago, these techniques should find them. Preliminary results from cores in Michigan and Pennsylvania show organic molecule spikes at the Younger Dryas boundary with isotope ratios that look similar to the ice core findings. Not identical, the lake environment introduces complications and potential contamination sources that ice doesn't have, but close enough to support the hypothesis. There's also renewed interest in searching for physical impact evidence if fragments of the object made it low enough into the atmosphere to create airbursts or surface impacts. There might be craters or disturbed geological features that have been overlooked or misidentified. Most impact craters on Earth get eroded away relatively quickly on geological timescales. 12,000 years isn't that long, but it's enough for vegetation to cover scars, for rivers to fill depressions, for human activity to obscure features. LiDAR surveying, which uses laser scanning to create high-resolution topographic maps that can see through vegetation, is being deployed across North America to search for circular depressions or unusual geological structures that might represent impact sites. The Burkle crater in the Indian Ocean is being re-examined. It's a large underwater crater discovered in 2006, tentatively dated to around 2,800 BCE based on sediment analysis, originally proposed as the impact site of a comet or asteroid that might have triggered historical flood myths. If the dating is uncertain, if it could actually be older, it might be connected to the Younger Dryas event. A fragment of the object impacting in the ocean, rather than on land, wouldn't leave an obvious surface crater, but it would create massive tsunamis and deposit ejecta across wide areas. Ocean sediment cores from the region are being analyzed for chemical markers. NASA's Planetary Defense Coordination Office has taken a direct interest in the findings. Their mandate is to identify and track near-Earth objects that might pose impact hazards. And while the Younger Dryas event is ancient history, the implication that fragments are still out there, some on trajectories that will bring them back through the inner solar system, makes this a current concern. Remember, the Euclid detections. 15 objects on inbound trajectories with arrival times ranging from decades to centuries from now. If those are fragments from the same parent body, we need to know their exact orbits, their sizes, their compositions, and what threat they might pose. The office has been coordinating with international partners, sharing data from the Euclid observations, the ice core chemistry, the orbital dynamics models. They're developing updated risk assessments, calculating impact probabilities for each of the known inbound objects. Most of them will miss Earth by comfortable margins, their trajectories passing through the inner solar system without coming particularly close. But a few, particularly the objects arriving in the next 100 to 200 years, have trajectories uncertain enough that close approaches can't be ruled out. Orbital perturbations from Jupiter and Saturn as these objects pass through the outer solar system could shift their paths, turning a safe miss into a dangerously close encounter. Ground-based observatories and space telescopes are being tasked with follow-up observations, trying to refine the orbital parameters and size estimates for the inbound objects. The more precisely we know their trajectories, the better we can predict where they'll be decades or centuries from now, and the more warning we'll have if one of them turns out to be on a collision course. The Vera Rubin Observatory, when it comes fully online later this year, will be particularly valuable for this work. Its wide-field survey capabilities will allow it to detect and track faint objects across large areas of sky, exactly what's needed to monitor a population of fragments scattered through interplanetary space. There's also the question of what we do if one of the inbound fragments turns out to be a genuine threat. Current planetary defense strategies assume we'll have years or decades of warning before a potential impact, enough time to launch a deflection mission. The DART mission in 2022 demonstrated that we can change an asteroid's orbit by ramming it with a spacecraft. The techniques exist, but they require advance warning, and they work better on smaller objects. A fragment several hundred meters across moving at interstellar velocity is a different challenge than a typical near-Earth asteroid. The energy required to deflect such an object, or the time needed to organize a mission, might exceed our current capabilities. That's assuming we even want to deflect them. And here's where the conversation gets philosophically complicated. If these fragments are genuinely from the same object that caused the Younger Dryas, they're not just rocks and ice. They're pieces of history, carriers of information about interstellar chemistry, about events that shaped human prehistory, about the dynamics of the outer solar system. From a scientific perspective, they're invaluable. The ideal scenario would be to rendezvous with one of them, study it up close, maybe even return samples. But the ideal scenario conflicts with the safety scenario if there's any chance of impact. Dr. Alessandra Springman at the Planetary Science Institute has been outspoken about the need for a nuanced approach. In interviews and opinion pieces, she's argued that we need to balance threat assessment with scientific opportunity. If an object is definitely going to miss Earth, we should be planning sample return missions, not deflection missions. If an object has uncertain trajectory that might evolve into a threat, we monitor it closely and prepare deflection options while still gathering as much scientific data as possible. Only if something is on a confirmed impact trajectory do we prioritize deflection over study. The public reaction to all of this has been mixed. The ice core findings got some media coverage when they were first published, mostly framed as new evidence for ancient comet impact. But it didn't break through to mainstream consciousness the way a current threat would. The connection to 3I/Atlas, the comet that passed through the solar system just a few months ago, got mentioned in some articles but wasn't emphasized. Most people who aren't following astronomy or planetary science closely don't know about the Euclid detections or the inbound fragment trajectories. That might change as more information comes out. There are ongoing discussions within the scientific community about how to communicate the findings, how much detail to share publicly about the objects heading toward Earth, how to frame the uncertainties without either minimizing real risks or creating unnecessary alarm. The experience with asteroid Apophis, which was briefly assessed as having a small but non-negligible impact probability before refined observations ruled out any near-term threat, showed how quickly public concern can escalate when impact scenarios are discussed in the media. Some researchers argue for full transparency, releasing all data and risk assessments as soon as they're available, trusting that the public can handle nuanced information about probabilities and uncertainties. Others advocate for caution, waiting until the uncertainties are reduced before making definitive public statements. The middle ground, which seems to be where things are heading, involves incremental disclosure. Publish the scientific findings in peer-reviewed journals, present results at conferences, make data available to researchers, but avoid sensationalized press releases or premature warnings about specific objects until their trajectories are better constrained. Meanwhile, the search for the parent mass continues. If there's a rogue planet or large planetary mass object at the center of this system, something holding the fragments in gravitational association, finding it is a priority. Not just for understanding the orbital dynamics, but because such an object, if it's on an orbit that brings it periodically into the inner solar system, could represent a long-term threat more significant than any individual fragment. A close approach by a planet mass object would gravitationally perturb everything in the inner solar system, potentially destabilizing asteroid orbits, disrupting comet populations, even affecting planetary orbits if it came close enough. The 5 candidate detections from reanalyzed WISE data that Dr. Volk's team identified are still being followed up. ALMA observations have been completed for 3 of them, Webb observations for 2. The data is being processed, but preliminary indications are that at least one of the candidates shows a thermal signature consistent with a Neptune mass object at around 90 astronomical units from the Sun. That's not confirmation. You need multiple observations to verify something like that, but it's encouraging enough that more telescope time has been allocated. If confirmed, if there really is a massive object lurking in the outer solar system, previously undetected because it's cold and faint and in a region of sky that surveys haven't thoroughly covered, it would be one of the most significant astronomical discoveries in decades. It would reshape our understanding of solar system architecture, raise questions about how such an object got there and how long it's been there, and potentially explain numerous anomalies in the orbits of trans-Neptunian objects that have puzzled astronomers for years.